Thanks for the kind introduction, Greg. And yes, I am still a university employee. So, we've heard a lot today about this spring system already, and I really appreciate the input from Dr. Ward and Rebecca Nunu and like sort of setting the stage for some of the things I'm going to talk about, given some good definitions and background on the geology and hydrogeology. This title is a continuing study. It points out that this is a continuing study because we started this project in 2018 and it's ongoing. So we have different phases of the project that have taken place, and I'll be outlining those for you. I want to make a point that the presentation today is really just on a small fraction of our data, not a lot of time, but the interesting thing is we've gathered a lot of data, and in gathering these data, we've also come up with a lot of new questions, and so that's always a fun thing to do. I want to emphasize that this is not just my work. It's a team of people. This is our current BEG team. We've had other former employees who've also contributed greatly. So I wanted to point out just a couple of photos here. I don't know if you can see them. It's a beautiful area to work, but sometimes it gets a little messy. So working out in these, in these water bodies. I get this question a lot, and yes, we do beg for money, but we are the BEG, the Bureau of Economic Geology, is we're part of the University of Texas at Austin, which has about 15 schools or colleges. The Jackson School of Geosciences is a fairly new school within the university, and then there are three parts of the Jackson School. Department of Geological Sciences, that's the academic side of things. Institute for Geophysics is purely research, and Bureau of Economic Geology is more applied research. And we also function as the State Geological Survey of Texas. We are primarily funded by SELF money. There is a small percentage of the money that comes through the state legislature, but primarily SELF money funding. And for that reason, we have a lot of people to acknowledge. First and foremost, the landowners. We would not be able to do this work if we weren't given permission by private landowners to access properties. And that's sort of a common theme that Rebecca Nunu was emphasizing also. I need to mention that from 2018 to 2020, the Apache Corporation funded our work. At the end of that funding period, we found ourselves with this fantastic monitoring system in this area, and we didn't want the data to stop being collected. So we found different ways of obtaining stopgap funding to keep the monitoring system going, which we're really happy to have been able to do that. I mentioned former BEG colleagues. Also, UT professors, various ones, have provided different forms of support. So I mentioned this, BEG work here, 2018 to 2021, but it's still ongoing. The objective of all the work is how to preserve the spring flow. And because there are a lot of demands on the water right now. We have both natural and man-made demands. Natural demands, lack of rainfall. During our initial study period, 2018 to 2021, there was no significant rainfall. So that really put a damper on things. There have also been multi-decadal industrial scale withdrawals of water, many different sources. As a result of our first phase of work, we did produce a contract report, which is publicly available at this address, and we published a paper. I think these presentations are all going to be available for everybody afterwards, so you'll be able to get these links at that time if you want. I want to emphasize that this is, it's definitely a group effort, and the results to date are not just our results. So what we have so far is a good hypothesis of recharge pathways going towards the spring system. There's a good understanding, as you've just heard from Rebecca, of geochemical indicators for sources of spring water. But what we think is needed greatly is more work on the physical hydrogeology, and that's what most of this presentation will cover. We have current limitations, lack of land access. We want to continue doing both geochemical and physical data collection, and I'll show you the area that we would really like to get into. Another limitation, as I mentioned, lack of rainfall, and also current lack of large-scale funding. I've listed other significant previous work here, namely U.S. Geological Survey started studying this spring system and recharge to the springs as early as the 1930s and published their work in the 1940s. There have been some more recent U.S. Geological Survey studies. Lots of grad students, undergraduate and graduate students working under Dr. Jack Sharp at UT. Rebecca referenced some of that work. The Water Development Board has done some regional studies out here too, and one of the things to note about the Water Development Board is that they continue to monitor both water quality and water levels. I'm cutting in and out here, I can hear, so let me know if I need to speak up. Anyway, other ongoing work, of course, Southwest Research Institute, National Cave and Karst Research Institute, the Nature Conservancy is supporting some work, Environmental Defense Fund, and Sul Ross University, I understand, is getting ready to have a meeting in January to bring different research groups together to try to collaborate better. Let's see, yeah, I got all that. So let's look at the big picture, and thanks, Dr. Ward, for introducing the local regional geology. I'm just focusing on Texas here. This map we're showing detail here in Trans-Pecos, Texas. Just for reference, here's Pecos, Balmorhea, Alpine. This is called the Trans-Pecos Volcanic Field, which is a lot of igneous rocks that were erupted around 40 to 25 million years ago. You've heard about the Salt Basin already, and I may have to be corrected here. Dr. Ward put that started forming 20 million years ago, not 25. So, but anyway, these are important features controlling the recharge. Geologic controls, Salt Basin, which I'll talk about a little bit more, and the Trans-Pecos volcanics are really important geologic controls, as I mentioned. So we have the Trans-Pecos volcanic field. I'm not going to read all this, and in a lot of these slides I do have many words, and I'm not necessarily going to read them all, but you'll have them for reference when you download the presentations later. Several of us have mentioned that the early hypothesis on recharge to this spring system around Balmorhea comes from the west, from the Salt Basin, and then hits the regional structures along the north side of the Trans-Pecos volcanic fields and runs this way into Balmorhea. So they noticed that the water in the springs is pretty salty. It's up to like 3,000 milligrams per liter TDS, but there are occasional freshening events where the water TDS drops, and That's been noted to be correlated with heavy rainfall over the Davis Mountains, which are right here in the northern part of this Trans-Pecos volcanic field. But most of the work to date has focused on groundwater chemistry, and there have been few hydrogeologic or water level data sets available. So that's what we're focusing on now. I just want to emphasize that there have been a lot of people that have worked on these igneous rocks in West Texas over time, and you can see their names and contributions if you're interested. Zooming in a little bit, again, here we are in Pecos, Van Horn, Northern Davis Mountains, Apache Mountains. This map shows locations in red where BEG has collected data in the past during that early study and also ongoing. Here are the Balmorhea area springs. Here's Balmorhea, Sandia, Balmorhea, Phantom. Hope you can see those stars. We collected water quality samples earlier in the study, and these two categories of in situ loggers and well intel sondes are ways of capturing water level data that I'll be showing. Again, we have limitations. Geographic coverage. So as you can see, the area we've covered in red, or the locations where we've sampled in red, are only about a fifth of this, what we call our total idealized study area. So our goal is to, as we continue to study these studies, is to get more access to properties out in this area. And I did notice, Rebecca, that y'all have 2 wells out here, so we're gonna have to talk about that, possibly getting access. And then, you know, we talk about this term TDS. I didn't know if anyone else was going to be talking about it before me, so I thought I would just provide simple terms of, you know, in simple words, what it means is that, you know, when water is in contact with rocks for a long time, it dissolves the rocks and it dissolves the minerals, and then the minerals dissolve into individual elements, and the isotopes in of the elements are what allow us to do fingerprint or track groundwater through the isotopic work that Rebecca was talking about. But one of the points we want to make here is that groundwater chemistry alone cannot really answer the questions of where the water's coming from, or it's more difficult. So like we said, we have these hypothesized flow paths along the north side of the Apache Mountains, down from the Salt Basin, through different gaps. This area is known as the Bolsone area. And so, you know, we just want to look further at the physical data. So this map is a similar area as the previous map. So we have Pecos, Van Horn, Northern Davis Mountains. But the base map here is the geologic units, and they're color-coded by the dots here are color-coded to correspond to the geologic units. So our oldest units are Permian in blue, and you have the Permian rocks outcropping at the surface. Cretaceous rocks are in green, the igneous, red, Bolsone over here in brown, and then Pecos Valley that we were just talking about a minute ago. A problem with trying to make a map like this, a potentiometric surface map, is that, you know, generally what you want to do is you want to have a lot of water levels measured in wells over a short period of time, knowing that all these wells are completed in one aquifer unit. Well, we can't do that out here right now. Based on the available data, which available data for wells that we know are tapping a specific geologic unit, and these are mostly from the Texas Water Development Board database, existing database, submitted drillers logs, and then some of our own data too. So I just compiled all the available information I could find on water levels from all these points and contoured them. Water flows from high elevation to low elevation. So you can see these contours, I hope. Here's so up here in the Davis Mountains, in the igneous rocks, we've got 6,000 feet followed by 5,000 feet, which means that based on water level data, and down to 4,000, we've got water flowing this way towards the springs that are highlighted with these stars. Over here in the Bolsone Aquifer, we've got water. It looks like it could even be coming out of the Davis Mountains around and up that part of the Salt Basin, the southern extension of the Salt Basin. If I don't have any contours around data, it's because they are no different from our closest contour. Up here in the Permian, we have a 4,000 foot elevation potential surface, and coming down to Cretaceous, a 3,000 foot. So we have indications from physical data that there is water flowing this direction. As you can see, we need more data in these areas that have gaps in them to better document this flow. So as I mentioned, limitations, not enough water wells, multiple geologic units with water levels measured over a 10-year period, which is pretty long, but you gotta take what you can get. And faults. I haven't mentioned the faults yet. All these lines on the map are faults in the region. This is essentially the Stocks fault that Rebecca was just talking about, and then I don't have the Rounsaville syncline on here, but it also comes down through this area. Next, let me show you this. I'm going to just showing the same base information on this small map right here. Got the geology background. Here's Van Horn. Here's the southern end of the Salt Basin. And what I've done here is I've overlain watershed boundaries on that base map. So, and also locations for rainfall data collection. So if you zoom, this is an enlarged version of this section of the map. So here is the Kent rainfall data location, and this is Mount Locke up near McDonald Observatory. We have a series of watersheds on the northern slope of the Davis Mountains. And these dots correspond to locations where we have data loggers measuring water pressure, water temperature, and in some cases conductivity, which is a proxy for TDS. These watersheds are Cherry Creek, Madera Creek, Little Ahuya, Big Ahuya, and Olympia Creek. And as you can see, they're all kind of flowing down towards this spring system. A couple of questions we have are, can we track water pulses flowing down these watersheds and then correlate those pulses of water coming down to freshening of the water in the springs? And the answer is yes, but we do need to do some more work to make it defensible scientifically, I guess. Second question is, can we see freshening in the Balmorhea State Park pool at times when we don't see water pulses coming out of the Davis Mountains? And the answer to that is maybe, but we need more data collection in farther west and northwest in the study area. This is kind of busy. I know it might be hard to read, but what I'm doing here is I'm showing logger response dates of logger responses, and a response means a big change in water level or chemistry from one of our data loggers in these different watersheds. So again, here's the Cherry, these are all the different logger sites in the Cherry Creek watershed, Madera Creek, Little Ahuya, etc. Different color codings are surface water sites versus groundwater sites. An X is just marking the date or, of the month and year of when we saw a significant response. As I mentioned, we did not have a lot of significant responses until recently, September of 2022. I think you all saw the same thing. And as you can see, we have a lot of X's here. And I'll show you some of these data, some examples of some of this data from these sites, both over the entire collection period and focused in on this time period. Another base map with geology. Zooming in a little bit more, these are the same data locations. These dots are the same data locations as I've shown on the previous maps. I've got stars around ones where I'm going to give you examples. Again, these are the Cretaceous carbonate rocks in green, tertiary igneous rocks in this kind of brownish red, and then yellow is not just the Pecos Valley, it's any alluvium. Like I said, I'll show you examples from these sites. So again, we have different types of sites at springs, creeks, and water wells where we have data loggers installed. We have different types of data loggers that collect different pieces of information. We have to have barometric control in order to correct our pressure readings on our loggers that are vented to the atmosphere, that are not vented to the atmosphere. So two examples we have a barometric control point up here, way up in the highlands of the Davis Mountains, and then we have another one down here near Balmorhea State Park. Just wanted to note that we've had more loggers in the past, as many as 36. We're now down to 22 field installations. Some of those we've lost through flooding. Some of them we decided just were not giving us valuable enough information to keep, going out there to maintain and download loggers, etc. I've talked about conductivity. Again, this is related to TDS as we've been talking about freshness of the water. Here's an example from, I'm calling this San Solomon Springs. This is at the Balmorhea State Park pool. I've heard different things. It's the San Solomon Springs system are all the springs that Rebecca was talking about, and then also people call the water coming up from the bottom of the pool the San Solomon Spring. But actually, if you're swimming around down there looking, you can see there's water just coming up from the bottom of that pool all over. I don't know if we can call it a spring, but there's a lot of water coming up in that location. So that's just wanted to clarify that for you. This plot here shows data from June of 2018 through June of 2023. This is a muted signal in pressure. Actually, this is depth that has been, this is pressure that has been converted to depth by correcting the data using the barometric pressure. This is done with Python coding. I cannot claim to be the Python coder. I leave that to my younger colleagues. But I have been able to at least use the code and change the dates and the depths and the scales and stuff like that. So it's a really nice way of looking at the data. So this top plot is depth versus time. This is conductivity versus time. And this is temperature versus time from one logger. We've got this, the Balmorhea State Park pool is a pretty big area. So if you have a change in pressure signal, it's going to be dissipated across the pool. So we don't see really big jumps, except for times like here when they drained the pool back in 2018. They drained the pool again in 2019. So if we look at these other signals, and these lines down here and these lines here are times when we were downloading the logger. But if you go along and look, again, you can see our first significant jump in pressure or depth of water over the logger was in the fall of 2022. At the same time, we had a nice drop in conductivity from over 3,000. This is a different set of units, microsiemens per centimeter, but from over 3,000 down below 1,000. That corresponds to like around close to, a little over 1,900 milligrams per liter down to 640 milligrams per liter TDS. That's a big drop. And so we also have a drop in temperature at the same time. So I'll show you some more data plots to indicate that we're pretty sure we know that these changes in conditions in the pool correspond to when we have pulses of water coming out of the northern Davis Mountains. So that's a pretty cool thing to see. Unfortunately, someone has stolen both of our data loggers out of the bottom of the Balmorhea State Park pool. We found one of our landowners found one by the side of the pool just last June when I happened to be here and said, I think you need to see this. We haven't found the other one yet, so we do have a gap in data. We have some new ones installed now. And we're talking with Parks and Wildlife about how we might prevent this from happening again, because these things cost like $2,000 to $3,000 a piece. Okay, another thing I want to note on these figures is that most of the rainfall occurs during the second half of the year. I didn't mention that these blue lines are rainfall amounts, and here's the scale for that. We only have plotted here right now only rainfall over Balmorhea State Park. There is also, we have other locations for rainfall data collection, and when we add all those to here, it gets to be a pretty messy plot, and you need to be able to blow it up a little bit better, but it's really interesting. So that's what I wanted to say about that. I'll move on here. So just wanted to show you, this is a zoomed in view of that same data from Balmorhea State Park pool, just from June through December of 2022, showing these big responses in conditions at the pool. Here are what our missing data loggers looked like. Here's one of our former coworkers installing the data loggers at the bottom of the pool. As I mentioned, we have three types of sites, springs, creeks, and wells. So quickly, I'll just show you examples of these. This is a plot, a Python plot. So Python plot means pressure has been converted to depth in the top plot from September 2018 to June 2023. As you can see, we have problems sometimes with data loggers not working properly, batteries dying, all kinds of things happen. But to note here, in Phantom Lake Cave, we've got this nice pressure increased depth signal in the fall of 2022, drop in conductivity, even bigger drop in conductivity than what we've seen in the pool, and also a drop in temperature. Over here, just so you can see it a little bit better, the time period from June 2022 to July 2023, this pressure signal represents about an increase of 5 feet increase in water depth over the logger in less than a 24-hour period. So as we know, that's a dangerous place to be, especially if when one of these floods is coming through. Corresponding drop in conductivity and temperature. A creek example. Wanted to emphasize the importance of doing these barometric pressure corrections in getting our data right. For example, here we have stage which is height of water over a data logger in a creek. Let's see. Right, this is April 2019 to January 2023. We collect data points every 15 minutes. Again, we have rainfall, we have response from the logger. There have been some smaller responses with water flowing down the creeks in the past, but the biggest one, again, is in the fall of 2022. This is a temperature log, and this is interesting because we can see When the creek bed is dry, the temperature fluctuates a lot during the day. When we're getting flooding events, you know, the ponding dampens the change in temperature. So it kind of corresponds to this rise here. So we know that the creek level rose and then water was ponded for a while. It then dropped back down, big temperature fluctuation, etc. These again are corrected for pressure, barometric pressure changes. I mentioned that the importance of that is, you know, we're still trying to get the barometric pressure just right, the corrections. So this is when it's a dry creek bed and we're showing almost a half meter of water over it. So we're also doing manual measurements to try to, you know, get these things to zero when the creek bed's dry. But so more work is needed on that. Just giving you examples of the different elevations of where we have our barotrolls, our barometric correction stations, versus the elevation of this logger. And so that's, again, more data compilation processing needs to be done. Example from wells. This is raw data. It has not yet been corrected from the Bigahuya set of monitoring wells. We have one here off in the distance that's only about 20 feet away from the creek, and it's only 20 feet deep. We have one here farther away that's almost, it's over 500 feet deep. I've got that, yeah, 560 feet deep. This plot here is pressure and temperature, pressure in blue, temperature in yellow. Starting, and so we can see, but it's not corrected pressure. So we have these big jumps. So you can see this is normally a dry creek bed, and we can see in, starting in August of 2022, we had these huge spikes, which tells us that there was water coming down the creek bed, and it shows up in this normally dry well that's right next to the creek bed. It's probably, this you know, shows like, you know, greater than 10-foot rise, but because it's not pressure corrected, it's probably a little bit lower, but it's still impressive. Here's a different type of response we see in a water well, in a deep confined system. We had this, okay, so here's the blue line. I know this is hard to read. We have the blue line, pressure along here jumps up during this flooding event. We actually had 2 flooding events, as we see here. And then the water level pressure takes a much longer time to come back to equilibrium. Analyzing this section of the curve will give us a lot of information about the storage of water in this system, the fact that it doesn't drop very fast. We also, on this plot, we have conductivity. This is really interesting. We had pretty high conductivity, so you can't read that scale, but up here it was around 3,000 microsiemens per centimeter. I got this backwards. So around 1920 milligrams per liter, dropping down to below 300, around 300 milligrams per liter TDS. So this is really interesting. It's telling us that we had a normal, like salty water that's been influenced by a big flush of fresher water coming in. Okay, in summary of the logger data, again, here's the background of geology, geologic units, Pecos, Texas, Van Horn, Northern Davis Mountains. In review, we have 2 hypothesized pathways, a regional pathway, which is coming from the salt basin, the saltier water that we normally see as base flow in the springs, and then with these pulses coming down from the Davis Mountains that correlate to the freshening events in the springs. You know, I was talking with a friend about this and said, well, you know, isn't this obvious that you've got these springs here at the base of the Davis Mountains? Isn't it obvious that that's where the water's coming from? I say, yes, but the water in the Davis Mountains is very fresh, and the water in the springs is usually very salty. So it's not an obvious answer to where the water comes from in these springs. But as we know, there are a lot of people working on trying to document what the story is. Just want to say thank you for your attention. Hopefully I didn't interfere with lunch too much. This is a photograph looking out from south of the Davis Mountains out towards the Salt Flats. Wouldn't necessarily want to be working there in the summer. Here's up in the Davis Mountains. This is a lower Cherry Creek well site. You can't really see the wells, but you can see we have a really nice place to work. Here's one of the creek installations. I don't know if you can see there's a logger bolted to the side of the rock there. And that's what the creek bed looks like most of the time, you know, except when we have these big pulses of water coming through. So in summary, you know, if we could prove up the groundwater recharge pathways and storage in the subsurface that we might be able to get information about from these well responses, we might be, and using both chemical and physical hydrologic data, so we need to work together, we might be able to more effectively preserve the springs. So, that's all I got.